Well, I think we can start. Welcome back, everyone. So we made it. We're at the halfway mark. Congratulations. It's not always easy to get here in any given semester, but this is a really pivotal week for us, not because we have any exam this week or anything like that. It's more because whatever we finish at the end of this week right here is going to determine the extent of exam two. So the last fully completed topic on this week will be our last topic on exam two. And that means this weekend I'm going to be converting over before even grading to showing what's the formula sheet going to look like attached to the last page of the exam. What are the exact sections for the coverage on exam two? And what should the sample problems look like? I'll get all those materials started to get posted on pretty much on Friday of the end of this week right here. That way you'll have some opportunity to get some studying in, some office hours in, that kind of stuff, get questions asked throughout this week. And this week we still have to cover content, but on the Thursday of this week, if there are review questions relative to exam two, I'll be happy to take them, no matter even if there are a lot of questions. So that's where we're at. We're in section 4.3, about halfway, I'd say, which means this is potentially going to be the last section that makes its way onto exam two, but we'll know definitely once we get to the end of the week on Wednesday. Any questions or comments at all, folks, with the announcement so far? Or questions to start us out? Okay, well, before we jump right back to section 4.3, I put something on my thumb drive called reminder in all caps, and that's a glaring reminder. And it was related to a student question, I believe asked by Michael Trosper last class on Wednesday. So let's take a look into this one. This is relative to homework assignment number, I believe it is, let's see, nested quantifiers, probably assignment 3.4. And this part of assignment 3.4, I've mentioned to other students, is probably the trickiest part. It's almost a theme in chapter 3 that if you're dealing with anything related to taking ordinary English and converting it into a logical statement using quantifiers or logical connectives, usually that's the hard problem. It's kind of strange in a certain sense. So the problem we looked into was problem number 12 specifically, but also as it compares to problem number 9. It's a weird set of problems. Problem number 9 is the slightly more natural one, where it says all comedians. It's directly talking about the universal quantifier. So we say for all x. And I've defined a new thing, u here, possibly just to help me make sense of all this out, of all what's going on between 9 and 12. U is supposed to be a universe of all healthy people, but I suppressed it on this one and just considered it to be in context for this one down below. Also notice the trickiness of problem number 9. It's easy to miss that this is an implication as well, all at the same time. When it says all comedians tell jokes, we have to say, take any X amongst the set of all living people. If that person is a comedian, then they tell jokes, giving the conditional there. But none of this is directly answering the larger question that was asked. What about this one? It says if someone, which kind of feels not too different than saying some people. If someone is a comedian, then they tell jokes. Really is a universal quantifier again. There's actually no difference between the statement 12 and number 9. One way to kind of think about it, this is what I didn't come up with at the end of Wednesday's class, is when it says if someone, we're not talking about at least one person, we're talking about everyone. We just frame it with a conditional if in front of it and then over here. But because we're talking about generically anybody amongst a set of all living people satisfying this condition, it's once again a for all. If you go this way, some people, this one is directly saying we're dealing with an existential quantifier. There exists at least one person or some person satisfies the property. Some people who tell jokes are comedians, so C of X implies T of X. So down below is kind of just the write-up of what we're saying here, pointing and clicking at stuff. But any questions at all, folks, with that closer look into this? Yeah, let me see. Some people who tell jokes, I think I got mixed up on the actual predicates themselves. Thanks for spotting that one. Should really go the other way, like you said. Should have been T of X. That's the telling jokes. So, that should have kind of clued me in. Comedians is C, telling jokes is T. So T of X implying C of X. Thanks for that correction there. Other questions at the moment with this one? Okay. Thanks for bringing these questions to class, by the way. I think in this chapter 3 with logic is really very tricky the moment you start to get into sections, 3.4, 3.5, the quantifiers, the nested quantifiers makes this all a little bit more foggy. So keep those questions coming. I feel like there's going to be lots of questions in this section as well, but that's pretty much a huge anticipation. The homework set is trickier probably than all the rest. So if you have trouble getting started with these, don't hesitate to reach out in class, before class, after class, office hours, or like I mentioned, even right as we're starting out class, it's a good idea to take a look into these. Great time to take a second look. But I think I ran out of announcements and comments so far. Here's where we left off. Well, not exactly, we're on example 4. But what was going on in example 2 was we were using this mathematical knowledge here about a way to define even and odd. It's not the only way to define even and odd, but it's a slick way to do it because if you have to prove something about evenness or oddness, you want to have a hook with algebra, and this allows you to do some algebraic things, this part on the right here. So we took this mathematical information, and the first proof technique was the so-called direct proof. We were asked to prove if the product of any two numbers is, let me start over, prove that the product of any two numbers is odd. We quantified the statement. We assumed the hypothesis that x and y are odd integers. This is what it would mean using the definitions above. We were meant to show the product of those two numbers is odd. So this is the conclusion we're going for. And in the direct proof, we have it. Thanks to the work above, that definition, we can translate even and odd into algebraic forms. Well, this is the odd algebraic form. Directly work with it, analyze the output, and see if it fits in this expression once again. Because we got twice something right here. Here's that twice something up here. And it's equally critically, because we got the plus 1, and because there's a 2 multiplying, all those features allowed us to say xy itself is odd. So that was our approach on the direct proof. Any questions at all, folks, with the really fast rundown on this one? Okay, our next proof technique was proof by cases. Redoing this content right here, we were proving for every integer n, the expression n squared plus n is even. And that's really hard to show because in the very last problem, we need a hook through algebra to really show the evenness of that expression. And just saying we're dealing with any integer, that's not super helpful because if we know n is even, we have an algebraic form to work with, n equals 2k. If we know n is odd, we have a different algebraic form, n is 2k plus 1. That means we did 2 proofs. Whatever the case was, even or odd, we showed n squared plus n happened to be even because it's twice some other integer. And that's the essence of proof by cases. These proofs, it's less about the mathematical content here, and it's more about the logic of how we're attacking these. So let's try out another one right down below. And this is where we actually left off. It says for all x and r, so any real number whatsoever, we want to show that the absolute value of that real number x is less than, let me try again. We want to show that x itself is less than or equals to the absolute value of itself. It's a hard statement to read out. X less than or equals to x is probably a better way to say it. When we quantify the statement, it is an optional step in the proof, but it gives you a good view of the landscape, what's going on logically. We saw that we have a universal quantifier on x and no conditions, which is unfortunate because the absolute value of x is naturally a piecewise function. But analyzing the piecewise function told us what the cases should be. We informed that case 1 should be x is non-negative. Case 2 should be that x is negative. This is an exhaustive set of cases in the sense that it really does cover all real numbers are. So if we can establish that equality both times, either in case 1 or in case 2, our work is complete. Well, let's get started then. This is the layout of the proof. In case 1, we're assuming x is greater than or equal to 0. We can now say this means if where the red dot was, we set an assumption, say a different problem, assume x is odd, we would still say this means, and then we would just say the essence of oddness, the algebraic form. Well, if we're assuming x is bigger than or equal to 0, we should go to our target. Our goal is to show that. So let's just calculate the absolute value of x and see if it fits into our progress so far. This means absolute value of x, because x is positive, is really just x by that definition there. And so let's return to the inequality and show if we can really establish it. Well, x equals x. That's not too earth-shattering. But if you go to this statement, x is also equal to the absolute value of x. And that means we really have a stronger statement than what's up here. We have that x itself, I'm not sure if that extra equals there was really super informative. Let me just back off one step. We have shown that x equals the absolute value of x, the statement over here, which then in fact implies x itself is less than or equal to the absolute value of x as required. Not a really earth-shattering step, but I think it's interesting that over here on the left by the red dot, that's a stronger statement than over here, but that is the statement that we had to prove, that x itself, because we have equality, this is true, it really is less than or equals to x. Recall, this is a compound statement. It really means x equals x in absolute value, or x is less than x in absolute value. As long as you show one of these is true, you're all set. And we showed that part's true. And so we were allowed to extend into the overall statement here. It's really less than or equals to x in this case 1. Well, we did it, folks. That's case 1 down. If we can show it holds in case 2, our job is done. If we run into any logical trouble here, well, maybe we made a mistake, or maybe the original assertion was wrong. We're expecting these are true statements, so let's work this out carefully. Assume x is now negative. This means, go back to what we're trying to show, x is still less than or equal to absolute value of x, so we calculate it. This means the absolute value of x is now negative x. We're down here on case 2 of the piecewise function. Now we can say, and so, let's think about this. We want to show x less than or equal to absolute value of x. So we really ought to start with x. So here it is. Now, what can we say about x? That x right there is negative. We said so in the beginning, right? So we have a negative value. That means it's strictly less than negative x. This just looks weird, so let's think about it. On this side, we're negative. We took the absolute value, which forced us positive. So on this side, even though the negative in front kind of tricks our brain a little, that's positive. So the direction of the inequality is right. And over here, gained through the piecewise function, negative x is absolute value x. So let's throw that in. So we can say this whole statement right here, mirroring the logic above, implies, well, there's transitivity of inequality signs and equality signs. And that's why we always want to connect them through. So now we can go on the very far left and say x less than, all the way on the right, absolute value of x. This is the most true statement, but we're weakening the truth on it and saying less than or equals because we're going for the overall statement up here, which would work with this one, case one, and case two simultaneously. So we were able to get to that conclusion for any real number you pick in the set of real number systems. This has been established. It's always true that x is less than or equal to the absolute value of x. I mean, we knew that, but writing up the details sometimes is a little bit trickier than you would expect. Here are the details. We can now say in either case, x greater than or equal to 0 or x less than 0, we have x less than or equal to x, absolute value x, I should say. So it ends the proof directly at that statement there. Here we're just stating the conclusion because if it's a proof by cases, we want to say once and for all, these are the only cases, and no matter what case occurs, we hit the conclusion that we are trying to hit. So we did it, folks. That's our second proof by cases problem. Any questions at all, folks, with the analysis of getting through this one? Okay, well, aside from the direct proof, where you just start with some mathematical, when you start with some mathematical content and proof of fact, that was our direct proof. Aside from proof by cases, I have a couple, well, really three major proof techniques left over. The next one is the good old contrapositive. I think this is a tricky one, so sections we've worked on this to really state what we're trying to say here. The definition says to give a proof by contrapositive of the implication phi, and let me try that again. Yeah, phi implies psi. We give a proof of the implication, not phi implies not psi. And the motivation for this is we go back to, say, this is section 3.3. We did a really interesting truth table. We kind of hinted that this is something that should come back. Let me see if I can find it. There it is. We have converse, contrapositive, and inverse laid out here. Here's P implies Q, the implication. And we were able to show right here, that's the contrapositive, logically equivalent to the original implication. Logical equivalence means the truth assignments that we get, or hang on. No, I'm looking at the wrong ones. It should have been this one and this one. Let me take a screenshot to try to clarify better. There we go. We were looking at multiple statements at once with this, so this will be a better screenshot to clarify. So this is the implication, which matches up this part of the definition below, phi implies psi, and this part, not Q implies not P. Let me fix that one more time. Oh, Microsoft is upset. Let's hope it returns. We get a moment of small mental break here. There we go. Microsoft's back, but doesn't like what I'm doing. Hang on. I think that screenshot was just too much for it today. Okay, aside from Microsoft complaining a whole bunch, here's the thought I was trying to convey. This right here is the contrapositive. Matching up with the contrapositive statement given down below here on the definition 4.22, we said when we were in section 3.3, these are logically equivalent in the sense that the truth assignments line up. And let's directly check that, true to true, false to false, double true to double true. So we are being told P implies Q is logically equivalent to not Q implies not P. And the magic of this contrapositive we have on the right is not that this is something you want to do each and every time you're trying to prove an implication, P implies Q. What this is more about is sometimes P implies Q is the harder statement. by a lot. Whereas if you looked into the contrapositive, your proof is almost immediate. This isn't always true, but if you select the right problems and do the right edits like we did down here to make them sound, suddenly the contrapositive is like your best friend in a proof technique. So that's what we're going to practice in the next couple problems. First, any questions, folks, with this logical equivalence here? Let's just say here for extra emphasis that that is the contrapositive as well. And let's give this a try then. So I made one fix right here. The original notes that only got corrected today was that said Z. It really should be any real number. So I picked two real numbers with the assertion that Y is non-zero. Since we want to divide, it says here, if X divided by Y is an irrational number, say like square root of 2, then either X is irrational or Y is irrational. And this is a true statement. It could be both. Keep in mind, these are ors that appear in logic, especially if it's a mathematical statement, are almost always inclusive ors unless it's said otherwise very specifically. So it could be both, even if we said either or. So how should we prove this? Well, we could pick a generic real number, a generic irrational number, and then, let's see here. No, let me say this a different way. If we were to give a direct proof, we would start by saying we have a number, it's expressed as X divided by Y. We know it's irrational. And then we'd have to show either one of these statements is true. If we can just get one to show that's true, then our work is done because of the or right there. But this is actually a pretty difficult undertaking. I'm not even too sure how you would start this kind of problem. This is one of those problems where the original question being posed seems correct, it seems logical and natural, but showing the actual specific details is not easy with this format of the statement. We're going to hit it with a contrapositive and see if we can exchange for something that is much easier to work with. But the trick with the contrapositive is you have to really view your statement as an implication in this way. So let's do just that. This part right here establishes the universe that our x's and y's come from real numbers, with y being non-zero. But when it goes if then, that's really just a if p then q type statement. So let's think of this part right here as the p, that either x or y irrational is going to be the q, and this is p implies q, the original direct statement. We want a contrapositive, let's hide that first. So we'll say that the contrapositive goes not q implies not p. And let's actually write out that statement. Actually, writing out your contrapositive is probably the most important proof technique of all, because if you're just trying to say it in your mind, that's really hard to work with. But if you've written it down, you are now able to see it, you're internalizing it even better, and it just gives your subconscious way more to chew on. So let's write out not q. Either x is irrational or y is irrational. You know, this is going back to section 3.2. Any volunteers for the negation, not q? While we're thinking about that, let me add just a little bit more detail. This is tricky in a certain sense because
by default, or just like the prefix, or
yeah, it'd be pretty much the whole statement right here, the not q has to apply to. So yeah, that's kind of a challenge, right? You're on the right track. We have to use something for logic that's going to allow us to negate this. Anyone happen to know what the trick would be? Let's view this from the land of a statement u or a statement U and V is always weird because it looks like an or statement. Let me go with a W. So U is going to be the statement, X is irrational. W is the statement, Y is irrational. There's a logical connective, the so-called disjunctive. Well, let's just call it or, that's easier. But what we want to imagine is, what if we negated it? What is the format of not U or W? Anyone see what should go on the right-hand side here?
I believe it would be not U and not W.
Yeah, absolutely. Good call on that. And this is by Dave Morgans. Well, one of his many laws. And then we saw it again with quantifiers. So that tells us, again, there's a lot to break down here. Just going from a contrapositive, all of our work in chapter 3 essentially is being leveraged into this problem. It's kind of impressive. So, I mean, it's a good one to go slow on and methodically. We're ready to write out the statement. If Q is a statement, either X is irrational or Y is irrational, the negation of Q is the statement that, let's see here, X is not irrational. That's just a way of saying it's rational. And at the same exact time, W is also not irrational. Let's say it in this more compact way. Both X and Y are rational. Let's use that if, make it seem like an equivalent statement as the original one up here. If both an X and Y are rational, then, so this whole part right here is not Q. Let me see if I can convey that slightly better. Okay, from this all the way out to here, right before the if, after, right after the if, before the then, that whole thing is not Q. Which will then imply not P. Not as bad, right? Not P would be, well, if P is the statement, X divided by Y is irrational. Not P is a statement, X divided by Y is rational. So let's say, write that in. X divided by Y is rational. So now my claim is, somehow, some way, this statement is really, really hard to prove. But change your entire frame of view, go to the logically equivalent statement for the contrapositive. You have to do the hard work of actually saying what the contrapositive is because we're about to prove it. But this is the easier statement to prove by far. And when I say by far, I mean miles. This is insane in a certain sense. So let's give now proof by contrapositive. Or we could say proof by contraposition, just another stylistic way of indicating our proof method. We're trying to prove this original statement right here, but in doing that proof, we're really proving this one. So let's start with maybe getting some extra space. I think we're gonna need some more space on this one. Oh no, hang on. Before I do that, try to Control Z this back. These really should stay right where they are if it's possible. Okay, let's take this whole thing down a new page. And back to our proof. Proving this statement right here, but really the contrapositive. Let's start by saying, assume not Q is true. What we'll actually write is assume X and Y, if they're rational numbers, that just means they're the element of the set Q. And good guidance on these symbols like Z for integer, Q that we just put down for rational numbers, R for real numbers, is all the way back in chapter 2. I think our first section 2.2 indicates these notations right here. So we're going to assume both X and Y are rational numbers. Now we have to say exactly what that means. It means they're fractions with non-zero denominators. So let's say this means there exists an A in a set of integer Z another quantifier that exists, b, in the set of, I want to make this strictly positive integers. I'll have a fraction x equals a over b. This symbol here forbids b from being 0 itself, which is helpful. And because a is any integer whatsoever, I'm not excluding this from being positive or negative. This can now be any fraction whatsoever. That was just for x, so we do it again for y. For y, same kind of structure, but different values. Let's say there exists u in z, exists b in z bigger than 0, such that y equals u over b. And hang on, let me try again. That shouldn't be b twice, right? We should allow for different denominators, or we haven't really looked into any possible rational number whatsoever. So let's say u over v, there we go. And by the way, there's still a problem with my quantifiers on row 2 specifically. It's not the existentials, it's the set z itself. One thing I should probably say to be really, really hyper specific and make sure we don't have any logical holes is observe when we're talking about y in a denominator right here, we've already imposed a huge condition. All the time, we can't divide by 0. So if we're considering x divided by y, we should also assert not 0 here. So this is the set of integers z excluding the 0 value. This is the set of integer z's only including the positive values. And that means y itself not equal to 0. So that covers one little loophole here where we may potentially divide by 0 if we're not mindful of restricting this set here just by a little bit. Remove the possibility of y being 0 itself. From then on out, let's see what we're going for next. We have the not q. Both x and y are rational. Then we just need to show x divided by y is rational. How do we do that? Well, we have the algebraic stuff right here. We just need to put it together and actually show it's a rational number by exhibiting the numerator is an integer, the denominator is a non-zero integer. So let's say, with not q done, we'll directly go over here and let's just write out then x over y. Well, this is just going to be take x, a over b, divide by y, u over b. Now, let's see here. B couldn't be 0 in this location, but when you go to do the actual division, it's a over b times v over u. Now, u can't be 0, but we plugged in that hole already by asserting it couldn't have been on the very onset. Multiply these through and we get a times v, divide by b times u. And our goal is to show that right there is a rational number. It may or may not be. Just because you wrote down a fraction doesn't say with certainty it's rational. For example, root 3 over 4 is absolutely irrational. So we need to say just one additional thing before we can get to our major conclusion. And that last thing is the numerator must be an integer. Let's check. We took a and b, they're integers, so a times v is an integer. Let's say, since AV is an element of Z. Now, the next thing we have to check is two things. BU has to be an integer, and it cannot be 0. So let's see. B was strictly positive. It lost the potential being 0. U is any integer that's not 0 itself. So the product of two non-zero integers is also non-zero. That's just the zero product property of the real number line. If a times b is 0, then a is 0, or, hang on, let me fix that, or is going that way. B is 0 is the property, but since this is non-zero, or excuse me, since neither a is 0 nor b is 0, we have non-zero here. Let's say a, b, and z. Bu is an element of z, excludes 0 itself, and this shows x over y is in Q, it's a rational number as required. So I feel like this proof here is tricky, not because of where it started, proof by contrapositive. It's tricky because the original statement was just not nice to work with at all, not in the first place. That's a tricky statement. It's almost as if to make this problem, someone took the statement you would normally think about, this one, they took the contrapositive of that statement and made the trickier question above. A lot of problems on learning proofs actually really go that way. It's kind of strange. But the whole problem of this is not as much the mathematical content. It's really just all about what was the proof technique, how did it work, and how did the logic that we did before, all of this stuff, really support that kind of proof. Any questions, folks, with any of those phases of this approach?
Yeah, when we
The
write
logic
it out
itself.
in quantifiers,
Yeah.
should it be the where it says E element A is an element of Z? Shouldn't it be EX instead of just E? And then EY for the second one?
Oh, I see what you're saying. So you're saying for this E right here, because we're talking about X, we want an X right there rather, is what you're saying. Is that what you're
Yes.
referring to? Gotcha. So this one was a little bit different in a certain sense. Because it is talking about X, sometimes we feel like something should go there. But what made this one a little bit different is that the X itself that we're trying to build as a rational number, it came in with two different components. To build the rational number, you needed the A and the B. So we had to assert before we even got to X that there exists such an A, there exists such a B, for which X could be re-represented as that ratio right there. So it was because X itself had those two components, the quantifiers were about those components specifically, and then building X.
Oh, okay. I think the colon just between the E and the A confused me, but I think we're good now.
Gotcha. You know what? You're right. That is confusing me too. That was a mistake, a typo that looked totally invisible, but that's really super important. Thanks for specifying that. To make this really right, I should have just said exists A right there, and I should have said just exists U right there. Thanks for mentioning that. The colon was really an easy way to get mixed up on this because that is
Yeah, it
a
was throwing me off.
yeah, it's throwing me off too now that you pointed it out. Suddenly my whole line here didn't quite make any sense anymore. That's a huge fix. Thanks for mentioning that. Other questions or corrections at the moment? Okay, and that really highlights that one small change of notation, the powerful power and impact of notation. We're relying on these structures that we copied and mirrored all along in chapter 3, sections 3.4, 3.5. Changing it now is a really bad idea. Let me just double check. I didn't slide into that on any other problems. Okay, yeah, that's the kind of structure we expect. You don't expect a colon right after the quantifier. It's like an incomplete statement if we did that. But we did, folks. This is the contrapositive. Thanks for raising that logical notation issue right there. It is actually major when you really look at it and its impact. What we'll do is we got to try it again, right? You can't just do one contrapositive and expect everyone has perfect knowledge on this. These are problems you have to try a bunch of times. So we'll do it one more time, at least in the lecture here. So here's our one more time, example 6. Example 6, if you think about what's going on logically with this, it's a lot bigger than it seems. Anyone see what part of this problem makes it a big problem? There's something in the statement targeting this sentence right here specifically. Something about this sentence is bringing in another logical form that we have to carefully consider to get the proof technique down just right. Anyone happen to see what it could be?
Are you just referring to the if and only if?
That's exactly what it is. And this is our first time encountering it in chapter 4. That if and only if is humongous as a statement. It means we have a statement that goes 11x minus 7 is even. I'll think of that whole statement as P. Another statement, x is odd. Let's think of that whole entire statement as Q. And sure, we want to prove P implies Q, but if it says if and only if, we also want to prove the converse. Q implies P as well. There's actually two proofs in this one out of nowhere. And here's the method that we're going to take. I claim that P, if and only if Q, is logically equivalent to the bigger, more cumbersome compound statement that works better in proofs that goes like this. P implies Q, and Q implies P. Our author does mention, though, occasionally with an if and only if, you can work this in a direct proof. You need to make a statement. Maybe it's P1, but what you say after the statement has to convey if and only if. Then you go to a statement P2, and then as you keep on making steps, you have to justify at every step that it's a reversible one with another if and only if. Until you keep on doing this, you end at Q, the conclusion, with that if and only if. And assuming that we're going this way, you also end at P as well. This is a really hard proof most of the time. The only times it really works out well is if you're just doing something in algebra, like 5x minus 3 is 7. Well, that's true if and only if 5x equals 10, which is true if and only if x equals 2. That works out. X equals 2 can be reversed. It also means 5x equals 10. It also means reduced by 3, 5x minus 3 is 7. But this kind of logic doesn't always work out well for these sort of statements. Oftentimes, when something is a little bit more involved, it's not just algebra you're doing or proving. You really want to break it down into two separate claims, verify them both independently. That would convey the and. And if we can do that, we have logical equivalence of P implies Q, or P if and only if Q. It's a better way to say that. So that's the approach we're going to take. We're going to use the logical equivalence rather than trying to do a direct proof with if and only if. Those are always extremely touchy. But first, how about a quick review problem as well? It's been a while since chapter 3, and we're seeing chapter 3 is really, really pivotal. So let's do a review problem where we do the following. Review. We will show this logical equivalence holds. Okay, let's do just that. Then, after we establish the logical equivalence of this one, it wasn't one we hit in section 3.3, I believe. So makes it for extra opportunity to review that problem. Then we'll dive into this one down below. So first, to prove a statement like this, observe we just have two propositions we're dealing with, P and Q. So we really only need 4 rows altogether, maybe 5, depending on how you format the table. We start by identifying the column for P, adding in truth values. This is the standard assignments that we used in chapter 3. Do it again for Q. This gives us all possibilities of truth assignments. Then we just look at P implies Q. There's only one way for P implies Q to be true. P implies Q is true. Actually, let me back up one statement here. For proving logical equivalence, might be a good idea to just do this one right out of the gate, and then do these two right here, right after. So P if and only if Q. Because it's logical equivalence, we only have true when the truth assignments are the same. That's when they're both true. or both false. This is easy to forget with these. We only get false when P and Q have opposite truth assignments, which is in the middle two rows right here. Now, I'm going to take a couple steps, do P implies Q, then Q implies P, and then we'll go to the actual thing we're trying to show, P implies Q and Q implies P. Okay, so that's our plan so far. Next, considering P and Q, look for the way it can be false. That's when P is true, Q is false. Then fill out true on all the remaining assignments. This one's trickier because we're going backwards. Look to where Q is true, but on the left, P becomes false. That's the truth assignment here on the second to the last row. That's the false assignment, rather. I think I said that backwards. So Q is true, implies P is false. Gives us a false here, but true everywhere else. And now we're going P implies Q to Q implies P. This is where we check for the logical equivalence. Only one way for this to be false. That's if we go from true to false. Thinking of this as the large structure. So false on this one. True here, vacuously true here, and true here as well. Now, to really double check that logical equivalence, we have to consider those logical assignments and those. We are not there.
Are we
Hang on.
comparing it with an and instead of what you originally did?
Oh, yeah, absolutely. I think that's my mistake on there. I did this whole table thinking of it that way. Thanks for the correction on that one, Catherine. That should have been thought of as the actual thing, and that fixes the problem here. Let me start over from scratch. Okay, P implies Q and Q implies P. Those implications just got a little too ingrained in my head, I think. This will be false only when we have at least one false assignment. False on this one, false on this one, true everywhere else where we have double true assignments. Okay, double checking what we have this time. True, false, false, true. Hey, we've got it. So it looks like it wasn't a lie. Thanks again for the fix on that one, Catherine. This is real logical equivalence, but what it means now is it conveys down into a proof technique. The slickest way to prove an if and only if is really divide and conquer. Show one direction, P implies Q. Show the converse direction, Q implies P. And that's all this is trying to say. Show both of those directions hold. So let's give this a try right away. One thing that's kind of weird about here is one of these directions is actually harder than the other. That's the forward direction, P implies Q. So let's tackle it head on then. Let's say here for the proof. First, we have a major division as proof. So I'm alerting in the writing here that this is the big major step. First, we show if 11x minus 7 is even, then x is odd. But this statement is kind of hard to show because if we were to start with this, 11x minus 7 is even, we would write out 11x minus 7 is 2k plus 1. Then we have to relate it back to x. You know, maybe that would work because we could solve for x. Let's actually show it that way. My thought was maybe go at it with a contrapositive. Wouldn't kind of make sense. We've only done one contrapositive problem, but the direct proof might work just as well. I'll leave it up to the class. Should we go for the contrapositive or should we try to show this just directly? Any volunteers for a way to go?
Could we do both?
We absolutely can. Let's start off with the contrapositive since that's really the big thrust of this whole problem example 6, not just the if and only if. So let's attack it first through the contrapositive. Using proof by contrapositive, Here we're alerting the reader that not only are we breaking this down into two different statements, but the main direction, if P then Q, we're changing the technique on this one and considering it's contrapositive. We really should write that down, or else whoever's reading this proof is going to be hopelessly lost. And that could be you if you're coming back to your work trying to see what you just did. Really good proof is a proof that you could put away, come back in a year, pull it out of your drawer and read it again and know exactly what you were doing. That's sometimes pretty hard. So let's try at least by writing down what the contrapositive would be. It would be the negation of this. X is odd, negation of odd is even. So we'll go if X is even, then we negate this statement, 11x minus 7 is odd. Okay, this was my main thought on this problem the first time I wrote it down, that this is a good direction to prove, but we'll try the direct approach as well, just for an additional view on this. But for proving that contrapositive, very first thing you do is assume P, this statement right after if, is actually true. Let's assume X is even. You want to say exactly what that means right here and now. Then there exists K in Z. So there exists an integer K, and here's the codes placed in the right spot, such that X is 2K. In other words, X is divisible by 2, forces even. We need to show 11x minus 7 is odd, so let's write that out. Then 11x minus 7, this is the more major algebraic statement, so we're displaying it in the middle. 11x minus 7 becomes 11, substitute in 2k for x, minus 7, so now we've got 22k minus 7. We want to show that we have odd here. That means we want a plus 1 on the end, so let's go 22k minus 8 plus 1. Associate the first two terms right here because we also want 2 times an integer plus 1, giving us odd. So from here, we can factor out that 2, leaving behind 11k minus 4 plus 1. So we've done it, folks. This value right here is an integer. We can now say since 11k minus 4 is an element of Z, that's just a really fast way of saying it's an integer, 11x minus 7 is odd. It being odd is because of the plus 1 right here, the times 2, and the fact the thing in the middle was an actual integer. That's what gave us odd altogether. And that's half the proof. That's showing P implies Q. I want to write down a really quick statement here just so I don't forget. Next, we must show the reverse direction. If X is odd, then 11x minus 7 is even. That's the converse of the original statement, not the contrapositive. Notice how different it looks. If X is even, 11x minus 7 is odd, versus if X is odd, 11x minus 7 is even. I mean, they sound the same, but truly different statements. But before we get to that one, to address that question in the class earlier, we showed this first, P implies Q, using the direct, or excuse me, using proof by contrapositive. Let's see if we can show it directly. For some reason, I felt like it was not as bad as a proof as I thought it wasn't originally. So let's see the direct proof of P implies Q. I'll put it here in orange just as kind of a comment in the middle. So if we're going directly, it means we have to show 11x minus 7 is even right away. Let's just say that. Assume 11x minus 7 is even. So that, just in one sentence, we'll say what it means to be even as well. There exists an integer k, so exists k in z such that 11x minus 7, that's the thing that's to be even, so it's equal to 2k. We need to take that information, show that x itself is odd. And again, the first time I saw this, I felt like this would be pretty hard, but I neglected to think ahead to realize if you can solve for x, maybe it's not that hard really. Let's see if we can solve for x or if we hit a snag. Then 11x will be equal to 2k plus 7. I've hit a snag. Here it is. So the direct proof, I guess it looks like it's nasty. If I just go to divide to solve for x, and I want to because I want to show x is odd, we get x equals 2/11 k plus 7/11. Now, I already have a problem right here, absolutely. The whole thing could still be an integer, but you need to prove this is an integer, and you need to prove that not only is it an integer, that 11 divides all of this if we put it under one fraction, that integer is also odd. It looks like the direct proof hits a humongous snag, so the contrapositive really was the way to go on this one. My thought of, oh, you could just solve for x and fix this, not good enough. It's kind of very finicky how some of these proofs will go. So this method fails. Well, it doesn't necessarily fail, but now we need a load of extra ingenuity to try to rescue it. It's a good idea to just abandon it and pick the easier method. I'll convey all that just by saying it fails at this step. Right there, we've got a big problem. Well, any questions so far, folks? We're halfway through the proof, going for the last statement down here. It's a good one for scooting down to the next page, I'd say. Okay, let's go for that second half then. Let's hide proof by contradiction. So for the second half, we're showing if x is odd, then 11x minus 7 is even. And really not too bad. We've looked at those statements at really the first time we did these notes. We start by saying, assume x is odd. Then for some k in z, some integer k, x would be twice k, that's even, so plus 1 forces odd. And last thing we have to show is then 11x minus 7 is even. Let's just say it out directly. Then 11x minus 7 becomes 11, 2k plus 1 minus 7, which is then 22k plus 11 minus 7. Keeps on going, so now you have 22k plus 4. We're going for even, so this looks good. We can factor out 2 from everything. This equals 2 times 11k plus 2. And our work is essentially done. We just have to convey the results. So then this happens since 11k plus 2 is an integer. All right, 11k plus 2, element of z. 11x minus 7 is even. At this point, we did it, folks. There's a lot to this problem just because of the if and only if. We really proved 2 statements all at once. We showed 11x is even if and only if it's odd, starting by the contrapositive and ending with this last half. This is in the backwards direction, Q implies P, or the converse. Well, any questions at all, folks, with the if and only if or the contrapositive? Really anything at all, but those are the main things we were discussing. Okay, Well, we've got 15 minutes for, I think the funnest proof technique at all, in my opinion, is proof by contradiction. And this depends totally on your viewpoint. I think this is a fun proof because, if you can derive a mathematical fact, I think that fact is awesome on its own. But some people have a very, very different take on this. Proof by contradiction doesn't give you a method nor an algorithm to show why the thing you're trying to show is actually true. So for people who want to look at a proof, implement it as an algorithm, say coding something up that can show the idea, the algorithm, the proof, they would absolutely hate proof by contradiction because it gives you nothing. A lot of times proofs are very informative, not just for the facts they show, but for an algorithm that it could reveal. But what does this do? To prove phi using a proof by contradiction, we assume the negation of phi. Derive a contradiction. We'll say that that contradiction emerged in our argument because of the assumption of the negation of phi. And if that assumption, the negation of phi is true, derives a contradiction, we say it's the negation of phi that's the fault of our contradiction. So phi itself is proven. That's the whole idea of proof by contradiction. We'll start off with the warm-up problem, example 7. Then we'll give it a proof of this one right here. This one takes a little bit longer, but it's an important proof because showing that root 2 is irrational is fantastically hard, but it turns out with the right proof technique, not so bad. So we'll attack that idea here through proof by contradiction as well. First, let's begin with example 7. This is our second example where we're getting away from even and odds and talking about rational numbers versus irrational numbers. This says, if x is a rational number, like 1 divided by 4, and y is irrational, like square root of 3, then x plus y is irrational. I think just about everyone would absolutely agree with that. Proving it is not easy if you need to show every single detail, but we'll prove it by assuming the contradiction. So here's how it begins. This is a humongously non-standard proof technique, so it's always a good idea to indicate when you're doing a proof by contradiction by just literally saying it. Proof by contradiction. The contradiction that we actually find could be anything. This is the hardest thing about a proof by contradiction. We want to derive a contradiction, but the statement itself does not necessarily inform what that will be. Take a look at this one, proving root 2 is irrational. There is no indication what that contradiction is for this either. It's kind of impressive in a way. But nonetheless, we'll try. We'll take our logic as far as we can. That's the reduction to the absurd. And the moment we find the absurd, we'll say, it's because we assume the negation of this statement right here. Okay, so it says, if x is rational and y is irrational, then x plus y is irrational. If we're going to prove this by contradiction, we have to deal with the negation of this entire statement. But our entire statement is an if-then. This is the P right here. This is the Q. So the extra idea that we need just on this problem, it's not really a proof by contradiction problem. It's just because our problem is a P implies Q. Next idea we're hunting for is the negation of P implies Q. And while you're thinking about that one, what is the negation of this? I think that's one we have done, so we don't have to re-derive a logical equivalence table. Let's see if I can find it here. It's somewhere. There it is. The negation of P implies Q. Let's pull this in. Let's get the red dot out first. It just looks ominous. So for this specific problem right here, This is a very, very informative logical equivalence, if I can get it to format right. Let's actually make that a little bit bigger. We can either look up here, which it turns out pretty small, or same statement down below here. Negation of P implies Q is P and not Q. Well, if that's the case, what are we assuming here? We're assuming P is true. Let's say that. Assume X and Y, X is rational rather. Well, that would mean X is in Q, set of rational numbers. Y is irrational. We don't write down this symbol a lot, but we can. That means Y is in the set of I, irrational numbers. Let's just define that since it's not has not been used a lot in this course. Set of irrational numbers. So we're assuming a rational number and irrational number. Then for the next part, let me minimize that properly. We assume, let's see here, the negation of Q. There's Q, so let's negate it. Also assume X plus Y is rational. So this part right here is negation of Q. That gets us started. So the truth table here just informs us what does the negation of all of this look like. And we really needed that because a proof by contradiction says we write out the negation of phi. Phi is the proposition, so we had to negate this entire statement outright. But now we're ready to get going on this one. Any questions at the moment, folks, with just the initial steps? Okay, well, let's start then with some of our assumptions. We made two big ones. One assumption is that we have an actual rational number here for X. The second assumption is that X plus Y is rational. So let's begin by saying these assumptions mean starting with X, there exists, let's go an integer A, so A and Z, there exists B in Z non-negative, so greater than 0, such that X equals A divided by B. So not too different so far than the first problem that we started off with today. For this part, Y being an irrational number, well, we have nothing for that. Irrational numbers are actually really vast. There are more irrationals than rationals, and I don't have any way to write down a formula for a generic one, not like this. So we just go over to the next one. X plus Y is rational is what we said. So for that statement there, we can say there exists U and Z, there exists V in Z non-negative, so greater than 0, such that now X plus Y, the sum, is equal to U divided by V. So we're done with the assumptions. We couldn't do anything with Y being irrational. We just have to recall that. Might be a good idea to just slap it with a highlighter. But now let's look at our overall statement. Let's see. We have, well, X is rational, Y is irrational. We assume the negation of Q in a proof by contradiction. X plus Y is rational now. Well, there's nothing really to show. We assume that that's true. What we're doing now is deriving a contradiction. Somewhere in this problem, we've used up all this information, but there's a contradiction here. Notice that we have X. We also have X plus Y over here. They're both equations, but in this equation, you could just simply substitute in X right in that spot. If we did that, we may get a contradiction. So let's try it out. Let's say, next, I don't know what's happening, so I'll just start by saying next. This is what happens next. Take x plus y equals u over v. We said that x is also a rational number. So this implies a over b plus y equals u over v. So what can we do with that? Well, remember, we said y is irrational, and it's right here in the middle. Let's solve for it and see if we can do anything with it specifically now at this spot. We pretty much have y cornered. The weirdest part of this whole problem, the irrational part, this now implies y itself is equal to u divided by b minus a divided by b, which is then equal to ab minus av divided by vb. We want to take a look at this form really closely. A, B, and V are all integers, so the element in the numerator is an integer. Let's say that right here. AB minus AV is an integer. We're essentially going backwards and thinking about, again, how do you build a rational number? Because this is starting to look rational. Look to the denominator, VB. They came from slightly specialized sets, the non-negative integers. And same concept, we're multiplying two non-negative integers together. The output, the product itself, is a non-negative integer. And these two observations here on the right tell us that y, expressed as a fraction, is not just a fraction, it's a rational number because of those two parts. That's what proves rationality. So let's say what this says. This tells us y is an element of Q. But now we have a really big problem. The real number system is partitioned by Q, the rationals, and I, the irrationals. And the partition means you take the union of both of these sets, it's the entire real number system, and they do not overlap. If we said y is an irrational number, which was reasonable, that's an assumption, but then we did some logic and said y is a rational number, at the same time it's irrational, that's a contradiction right there. And the contradiction occurred because we assumed P implies Q is false. The statement assume X and Q, Y and I, and X plus Y rational was just this logical equivalence, the negation of the implication. So all we now need to say is we found a contradiction and it implies the original statement is true. So let's finalize those comments. Y is in Q, but this directly and severely, let's just go with directly, contradicts Y and I. Oh, that was supposed to be a highlighter. Sometimes I think it's a lag and the tool just doesn't switch to the next pen or highlighter, but who knows? Now we can say here, this contradiction occurred by assuming which part? If we were going to give a direct proof, we would assume X is rational and Y is irrational. And then we would try to show that this is true. We assume the negation of that. That's the not Q right here. And because we arrived at a contradiction by assuming that, assuming X plus Y is irrational. Yeah, I almost thought I had enough space. Let me see if I can get a little bit more in here. Sorry for the sudden scrolling. This contradiction is occurred by assuming X plus Y is irrational. Excuse me, that's backwards, is a rational number. Therefore, X plus Y must be irrational. And finally, that's the whole write-up of this. If x is rational and y is irrational, x plus y is irrational, is what we landed on here. We did it by fully going for a contradiction and showing the contradiction emerged only because we assumed not q. Therefore, not q must be true. X plus y has to be rational. It's a fun proof, but it's also frustrating in the sense that if you wanted to take this whole idea and implement it as an algorithm or as a concept in hardware, this gave you nothing. It just showed you that there's a way to derive a contradiction by assuming the negation of the whole statement. But at least we can prove statements even when a direct proof is hard, and this is one of those methods. Any last questions at all, folks, on finalizing this one? Okay, sorry for taking the extra time today. Usually I try to end at least a minute before the hour. But when we come back next class, we'll finish off the last couple problems on these notes and look into a couple more problems in section 4.4 to round out the chapter. Any last questions at all, folks, before we officially call it a night? Okay, have a great night, everyone. I'll see you all in Wednesday's class. Here's these back for you, Denny.